Hey guys, today we'll be working with separable first order differential equations. We'll start off with one example with this expression right here, where f dy over d of x is equal to x cubed over y cubed. Our first immediate step is to bring the variables within their own categories. I want the x's with the x's and the y's with the y's. So let's cross multiply, and as a result we get the following expression right here. Now we can actually integrate the two to get rid of the d's, and as a result we get the following expression as this right here. Now what can we do from here? It turns out we can actually multiply by a common factor of 4 to this entire system, and as a result we're not dealing with fractions anymore. And when you add two constants together, what ends up being a sum? It turns out adding two sums just create another constant. So we'll consolidate our 4c's, and this is our expression. Now, as a ease of finding our general solution for this differential equation, we want to solve it such that it's y equal to. In this case, it's y to the fourth. So what can we do to get rid of that fourth power? It turns out we can raise this whole system to a fourth. So it's going to look a little like this. And once I clean that up, let me just clean up everything else right here. It turns out that when you raise the whole system to a fourth, you actually get the general solution. Now, while you may have the general solution, you may be working a problem where you are given the x value and the output, such that you get the following displayed in blue, where x is 2 and y is 0. And with the given point, you will have to find the value of c. So let's actually just plug in our values. It's a straightforward process. So 0 is equal to 2 to the fourth plus c, all of which is raised to the 1/4 power. And 2 to the fourth is 16. So without doing some further math, what would c have to be such that it produces an output of 0? It turns out c would just have to be negative 16. Now, when you have the x and y value and the value of your constant, what you actually have is none other than the particular solution at a specific point in time. So that's one way to solve, or that's one example of a separable first order differential equation. Now let's begin with another problem. Provided that we already have an initial value set up. So we have z prime is equal to y times z, which is also the same as d of z or d of y is equal to y times z. From here, let's bring our variables to their respective corners. So I want our z's in one side and our y's on one side. So the best step would be to simply multiply everything by, divide by z, and then multiply the whole system by d of y. And as a result, we get this expression. Our next step would be to integrate. And let's keep in mind that we are working with indefinite integrals. So as a result, this means we have to include our constants. Alright, now, do keep in mind that our y variable is our independent variable. So why does that matter? Because we have to have this solution set up such that z is equal to a specific function. On top of that note, if we were to subtract a constant from the constant, what would that be? What would the result be? It'd merely be another constant. So this is our following expression if we consolidate our constants. And our next step would be to isolate z. When we're trying to isolate the natural log of a given value, we tend to exponentiate both sides. So it's z is equal to e to the power of 1/2 times y squared plus c. And we now have the general solution. Now, if we were tasked with finding a particular solution, we would simply plug in y at 0 and z at 1/2. So it would look like the following, where 1/2 is equal to e to the given power. From here, we would have to solve for c. So our y is 0, so 0 squared is still 0, and anything times 0 is 0. As a result, we get 1/2 is equal to e to the power of c. Now let's take a minute and think about it. Do you already know what c is going to be? And would you believe me if I said c would have to be the natural log of 1/2? It's okay if you don't believe me, because we'll still work out the process. So, when we're isolating natural logs with given functions, we tend to exponentiate both sides. The same also works conversely speaking. We can take the natural log of both sides to isolate a given variable within an exponent. As a result, the natural log of 1/2 is equal to c. Now that we know what c is, what's next? Well, with the identity of c deduced, you now have the particular solution as well as the general solution. Okay, so this problem is going to require a little cognizance about your trig identities, and you'll see why. So we're given an expression where dy over dx is equal to negative y squared minus 1. And our initial conditions are set at 5 and 0, where x is 5 and y is 0. So to begin, let's try to multiply the system by d of x. So we actually get this expression right here. And if we were to integrate both sides, why would that not be a good idea? And it turns out the expression negative y squared minus 1 is on the wrong side. So let's multiply the system by its reciprocal, and we get the following expression. Now, recall my statement where you may need to remember your trig identities, such that when you integrate both sides, you should keep this in mind, where the derivative of the arc cotangent of x is equal to 1 over x squared times negative 1. And with that in mind, when you integrate, you get the following expression, where you have the arc cotangent of y is equal to x plus c. You'll notice that I consolidated the constants prior, and now we still gotta isolate y. And to do that, let's multiply the system by cotangent. As a result, we not only get the general solution, but we're on track to deducing the particular solution. So, with the general solution acquired, we plug in our x for 5 and 0 for y. And now we have to find a constant. So, once again, you do need to know your trig for this problem. At what angle does cotangent equal to 0? Try to refer to your unit circle. And once you do that, you'll understand that cotangent of 0 would be pi over 2. And actually, it should be cotangent of pi over 2 equal to 0. So let me just fix that up for you guys. So yeah, it should be the other way around, such that cotangent of pi over 2 is equal to 0. And there we go. So with that out of the way, 5 plus c has to somehow equal pi over 2. And from there we can solve for c, such that c is equal to pi over 2 minus 5. And the next step is to plug in your value for c into the general solution such that you now have acquired the particular solution at a given set of points.